Good day, everyone. This presentation is about estimating the sensitivity of water yield potential of small watersheds in the Philippines, an application of InVEST water yield model.
My name is Trespalacio, and on behalf of the team, I will be presenting this study. The Philippines is geographically situated near the area where strong typhoons are born. Thus, it is expected that the country will experience more frequent and stronger typhoons as the effect of the climate change is manifested. The Philippines is already facing the impacts of climate change that threaten to undermine our development goals and exploits the vulnerability of poorer communities. The graph shows the increasing trend of the country's annual precipitation from 1910 to 2020. This affects the water yield of the landscape, which varies based on the biophysical characteristics. Among the various ecosystem services that humans enjoy, the provision of flowing fresh water is crucial not only to the natural systems, but to humans' day-to-day survival as well. Various related studies have come with an agreement that water yield is affected by the biophysical characteristics and anthropogenic factors, including human-induced climate variations and land use distribution. Now let's talk quickly about the model. InVEST water yield module is governed by the Budico hydrological method, wherein the amount of water after actual evapotranspiration is excluded from each grid's precipitation in order to compute for the value of water yield per pixel. Furthermore, the model's design is for the quantification of the relative yields of different catchments. It is also sensitive to model changes in the drivers. However, its ability to reproduce empirical observations is still tested. Although the InVEST has been widely used to map ecosystem services in different countries around the world, its application within the context of the Philippines is still limited. The image is an author's keyword analysis, which shows that in the field of water yield research, climate change and stream flow are the most widely used terms. It can also be observed that climate change has more association with the stream flow. It is also worthwhile to notice that among the many software and models used, only the SWOT appeared, which suggests that other tools are not explored enough relatively. This justifies the model choice of this study, considering that the InVEST model offers a more user-friendly interface and requires a less complicated data input. So the objectives of the study are to quantify the change in water yield that can be attributed to the land use land cover type per basic spatial unit, and to understand the impact of climate change through precipitation to the water yield potential. We would like to set your expectation that most of the inputs used in the model are global data, since we were not able to find local data sets. Validation of the results was not conducted since we were challenged to search for observed data from stream gauges. This is the location of the watershed. Balanak and Santa Cruz watersheds are adjacent catchment areas located in the southern east part of the Laguna Lake. The watersheds lie within the municipalities of Rizal, Nagcarlan, Dilio, Magdalena, and Mahayhay in Laguna Province, and in Candelaria, Sariaya, and Tayabas City in Quezon Province. Balanak and Santa Cruz watersheds roughly cover about 65.75 kilometers square and 80.75 kilometers square, respectively. Both of the watersheds are prime agricultural areas for rice, corn, coconut, vegetables, and more. The watersheds are also a substantial source of water, particularly for the municipalities of Mahayhay, Dilio, and Nagcarlan. This implies that the water-related ecosystem services in the area is crucial. This table shows the inputs used in the study and their respective sources. In order to compute the annual water yield per pixel in the watersheds, the model was run using this formula. On the other hand, the image in this slide graphically represents how the model works. the model or the amount of water running off each pixel as precipitation, excluding the one that undergoes evapotranspiration, is determined. If you look into the image, the only colored aspects of the water balance were considered. We have also subjected the model to test its sensitivity using the different scenarios. It is shown in the slide. The baseline scenario was done using the 2018 annual precipitation data. In scenario 1, the rainfall was increased to 0.04%, which is the average rainfall change from the years 1900 to 2000. In scenario 2, the rainfall was increased to 0.34%, which is the standard 30-year average used in the climate studies. Scenarios 3, 4, and 5 are increased in 4, 5, and 10% respectively. So these values were considered in order to check the extent of the water yield when subjected to drastic increase in rainfall. Lastly, scenario 6 was a decrease of 11%, which was based from the projection of PAG-ASA for the years 2006 to 2035, using the observed baseline data from 1971 to year 2000. In order to dissect and better understand the influence between precipitation to water yield according to land use land cover types, the total water yield potential per LULC type and the mean water yield per LULC type under the identified scenarios were computed. We would like to show you the spatial distribution of the LULC types present in the Balanac and Santa Cruz watersheds for the year 2010. And this one is for the year 2015. This graph shows the land use land cover change from 2010 to 2015. This suggests that there has been a significant increase of the perennial crop. An increase in closed forest can also be observed. Albeit not as massive as the perennial crop, built-up areas have also been increasing over the past years. If this trend continues, it can be expected that the perennial crops, closed forests, and built-up areas will continue to increase in the expense of annual crop, brush and shrubs, open forest, and wooded grassland. This is the water yield potential estimation for the Balanac and the Santa Cruz watersheds in the base scenario. The highest water yield potential for both watersheds are the closed forests. But take note that these are the areas which receive the most precipitation. This slide shows the results of the total water yield potential for the base scenario. In Balanac watershed, perennial crop has the most total water yield potential at 538,628,463 millimeters. But take note that it also has the greatest land use land cover distribution at over 70%. This is also the same with Santa Cruz watershed. The perennial crop has also the greatest total water yield potential at 548,976,74 millimeters. It also has the greatest land use land cover distribution. The pooled data compounds the magnitude of the water yield potential that perennial crops provide. However, if we take into account the mean water yield per hectare as shown in the figures in this slide, built-up areas have the most mean water yield in Balanac watershed, which is about 184,730 millimeters per hectare. In Santa Cruz watershed, however, grassland has the most mean water yield at 214,120 millimeters per hectare, despite having a land cover distribution of less than 1%. It is worthwhile to note that the ample grassland cover in Santa Cruz watershed is located in Mount Banahao's higher elevation, which received the highest rainfall within the area. Next to grassland is the built-up area that has the highest water yield per hectare at 177,580 millimeters in Santa Cruz watershed. The pooled data showed that grassland remains to be the leading LULC type with the greatest mean water yield, followed by the built-up areas. For both watersheds and in the pooled data, the perennial crop has the least mean water yield per hectare. Let's discuss further how precipitation affects the water yield in the baseline scenario. So these graphs in this slide shows the three scenarios wherein land use land cover types were adjusted to determine the mean water yield potentials per land use land cover type if the vegetation in the grassland and forests were not considered. So the results show that the water yield for the supposed grassland would have been way higher had the vegetation influence of grassland and forests are removed. That is for Santa Cruz watershed. Now, in Balanak watershed, the graph shows that the mean water yield in open and closed forests increased significantly if their vegetation properties were removed. This implies the importance of the role of the vegetation to the potential effect of precipitation in the context of water yield. These are the results of the water yield potential estimation for Balanak watershed under the 6 scenarios. The perennial crop remains to have the most water yield potential, while built-up areas have the most water yield in terms of mean water yield per hectare. The behavior of the water yield remained relatively the same across all scenarios. For the Santa Cruz watershed, perennial crop has the most water yield potential across all scenarios. Grassland has a very minimal total potential water yield since its area is relatively minute compared to the other LULC types present in the watershed. However, if we take a look into the mean water yield per hectare, it has the most volume that can be attributed to its location, which receives one of the most rainfall. Built-up area comes next to grassland. In conclusion, the results of the study conforms with the common knowledge that vegetated areas have the least water yield potential since vegetation has the most water holding capacity that prevents significant fraction of surface from running off. As most water yield related studies have mentioned, precipitation has significant influence on water yield. This is demonstrated in the case of Santa Cruz watershed, wherein grassland surpassed non-vegetated areas in terms of mean water yield, since it was located in the area which received one of the highest rainfall. The same is true with the open and closed forests for Balanak and Santa Cruz watersheds. They yielded greater water yield primarily since they received the most rainfall. This means that despite having better LULC types, the drastic increase in precipitation as induced by the effects of climate change will still result to higher water yield. Generally, built-up areas have the most water yield potential. This is a crucial characteristic of an LULC type, especially in the light of climate change, wherein it is expected to have more frequent and more extreme rainfall events. This implies that the more impervious areas there is also an enhanced water yield potential that may ultimately cause or exacerbate flooding incidences. With that, a more cautious approach must be considered, especially when planning future land use conversions. Considering the increasing trend of built-up areas that was shown earlier, it is best to consider how the possible increase of built-up areas in the future might affect the water yield in the landscape. Considering the limitations that we have reluctantly compromised, we believe the study can be improved further by validating the results of the InVEST water yield model using gauge-derived data. It may also offer more accuracy and more tailor-fitted results to the Philippine context if local data is used to minimize interpolation that may have led to certain degrees of inaccuracies. In behalf of the team, I would like to thank everyone for your time and attention.